Hi and welcome back again. Today we're going to be looking at fuel cells as a source of energy. So we've looked at fuels such as fossil fuels, oil, biodiesel, biofuels and everything like that as a source of energy. Subsequently, we've looked at galvanic cells as a source of energy and how they can be primary or secondary cells, so how we can recharge secondary cells and have them as a continual replenishable source of energy as long as we can recharge them from an electrical outlet. Now we're going to look at fuel cells. These are an interesting form of galvanic cell, which we're going to look at as an alternative for things like transportation, so cars, uses by NASA, submarines, and things like that. So let's get started. So these are the key things that VCAR wants us to know. That is, we have to be able to answer questions relating to the design features of fuel cells. Okay, this will include, as we'll point out, porous electrodes, the idea of gaseous reactants, the cell efficiency. We don't need to know the specifics again of exact cells, but we do need to know the common structures and features of fuel cells and what sets them apart from galvanic primary and secondary cells or other cells. Okay, so you can expect compare and contrast questions with things like this and being able to talk about which is best in terms of environmental impact, efficiencies, and other aspects of a question. So, in fact, we have a key knowledge statement that says the comparison and use of fuel cells and combustion of fuels to supply energy. Okay, and we need to be able to talk qualitatively about energy efficiencies as well as things like safety, fuel supply, so how it can be stored, how it can be transported, and things like that. Its relevance to the production of greenhouse gases, applications, and other pollutants. The comparison of these fuel cells and galvanic cells with reference to definition, function, design features, energy transformations, energy efficiencies, and applications, which means that you want to be using things like Venn diagrams, tables, and ways to summarize the similarities and differences between these cells as you go in your notes. So fuel cells are a type of galvanic cell. These are where reactants are supplied continuously from an external source. So previously with primary and secondary cells, they have been contained within a battery, or we've had two half cells and the external circuit being contained. So in a galvanic cell, we've had the two half cells with electrolytes and the electrodes. But we have finite electrolyte and finite electrodes in these. In the case of fuel cells, our reactants are going to be pumped in. So they're going to be in the form of gases, which can be pumped into the cell. So as long as they are being pumped in, we will see the production of energy. The battery's not going to run flat. The cell's not going to run flat. We see transformations of chemical energy directly into electrical energy. So this is the same as what we do with a galvanic cell, chemical potential into electrical. And we can see efficiencies up to 80%. So these tend to range depending on the cell from 50 to 80% efficiency. With galvanic cells, we can see high efficiencies as well in the realms of 60 to 90%. So we are talking, because it's a direct transformation, we're not losing energy a lot along the way, we have high efficiency. We do need to pay attention to whether or not our fuel cell is alkaline or acidic. And in alkaline fuel cells, we use pure oxygen and hydrogen gases as reactants and potassium hydroxide as the electrolyte. So this is one of our example cells. And we get the half equations from that from our electrochemical series. So if we have a look at a simple design of a fuel cell, one of the main things that we need to do is always check if the electrolyte is acidic or alkaline. This will determine which of the oxygen half equations we're going to use from our electrochemical series. If you grab out your electrochemical series and have a look, we actually have two equations for oxygen. One that will be at around 1.23 Okay, and this will have H plus in the half equation, and we use this one if it is acidic. The other one comes in at around 0.40, and for this one, it will have OH minus in the half equation. This is our alkaline. We need to make sure, if it says it's an alkali fuel cell, we're using this one. If it says it's acidic conditions, we're using this one. This is a common mistake, and we want to make sure that we use the right half equations when talking about fuel cells. If we're talking about a hydrogen-oxygen fuel cell, each cell is going to produce approximately 1 volt, and we need to connect them in series like we saw with the lead-acid accumulator to get greater voltages. There's a couple of differences in the way that these operate, and that comes down to the electrodes. The electrodes of these cells are generally layered or porous, i.e. they have holes through them that the gas can move through. They are generally impregnated with catalysts because these will often require catalysts to get them to work efficiently. And we need to keep the fuel and the oxidant apart, but still allow contact with the electrolyte. So what you'll notice here is the hydrogen comes in one side with the electrode, which is porous, so will allow transfer through here into the electrolyte, and the oxygen comes in the other side and will come in through here. So it means that the two don't come into contact. They will permeate through this into contact with the electrolyte, and then we actually will get water as our output from the cell. You'll notice here that the fuel, hydrogen in this case, is at the anode, and oxygen is at the cathode. Remembering, if oxygen is present, it will be the oxidant, so therefore it will be reduced, meaning that this process will occur at our cathode. So we should always be, regardless of the fuel cell construction, oxygen should be at our cathode, and the fuel, which is being oxidized, because essentially it's going to be just like a combustion reaction where we see oxidation of the fuel, will be at the anode. So there's a number of different fuel cell examples, and you will find this in your textbook. You don't need to memorize their operating temperatures or efficiencies, but you do need to notice some basic trends. You will see here that the standard alkaline fuel cell, which uses potassium hydroxide as its electrolyte, so we're going to have OH minus present, gives about a 60% efficiency and runs at a much higher temperature. One of the things about fuel cells is that they run at a higher temperature to what we see typically in galvanic cells. Some of them, like in the solid oxide fuel cell that we see down here, as high as 600 to 1,000 degrees. Because this is alkaline, we're going to be looking for the half equations on our electrochemical series that produce or use OH minus. We can also use methanol. This has a polymer membrane, so it's a specially designed polymer, as in the fuel cell construction. We tend to see these used in mobile phones and laptops. This is not specifying an alkaline condition, so we now can use methanol. We use cohes to balance the methanol half equation, and then the cathode is going to be oxygen. Essentially what we're seeing in a fuel cell is a combustion reaction of the fuel happening, but we're controlling the oxygen being present at and the fuel coming into contact through the electrolyte. So the electron transfer that is occurring is going to produce the electrical energy. Okay, I suggest you have a look at these different half equations, make some notes, make particular attention to where the alkaline and the acidic conditions are, but you'll notice these are just any time we're burning something other than hydrogen, we are just producing CO2. Okay, again, because this is essentially a combustion reaction of the fuel at the anode. In the case of hydrogen, we don't produce CO2, we're just producing water, which makes it more environmentally friendly because we don't have the carbon dioxide emissions or other sooty particulate emissions. So this is a closer look at the alkaline fuel cell. You can see that the hydrogen is coming through. It permeates through the electrode, coming into contact with the electrolyte. Okay. And the oxygen does the same. These catalysts facilitate the reaction, which break apart, basically ripping the hydrogens off the protons from the hydrogen. The electrons are pumped through the cell over to the other side, where we pick up oxygen, which reacts with the hydrogen, and we produce water. So the output of these cells is air and water vapor. So at the anode, hydrogen gas is reacting with hydroxide to produce H2O and 2 electrons. This is from your electrochemical series. At the cathode, oxygen is reacting with water and 4 electrons to produce 2 OH-, again from your electrochemical series. So overall, we have hydrogen reacting with oxygen to produce H2O, and this is the combustion equation for hydrogen as the overall equation. So the formation of hydrogen gas for fuel cells determines if the process can be considered renewable or greenhouse emissions free. Steam reforming accounts for 95% of hydrogen production, i.e., we use things such as methanol and water to produce carbon monoxide and hydrogen gas. The carbon monoxide is then collected and further reacted to produce CO2 and hydrogen gas. These require catalysts in order to occur. We produce hydrogen this way as it has a lower enthalpy of combustion than CH4. So we need to use the catalyst in order to get it. Advocates of this process consider it a better alternative to natural gas, i.e. using the hydrogen here. And I want you to think of reasons why they might consider that. So think about the role of methane in global warming, capture emissions of cells, and various other things like that, and see if you can come up with some reasons why they say that even though we're using methane to produce hydrogen, why would that be better to using natural gas to power turbines? One of the problems that we have with hydrogen for fuel cells is hydrogen storage. Hydrogen is highly explosive, okay, as a gas. So we don't use the term volatile because that refers to the ability for something to turn into a gas. Hydrogen is an explosive gas. So when mixed with oxygen in the air, it doesn't take much of a spark source to make it combust and explode. Okay, so they have come up with ways to store hydrogen, such as liquid hydrogen or compressed hydrogen, to make it safer for larger applications with fuel cells. The problem with these is that they require complex engineering or significant energy input to liquefy it as a fuel, and being able to store it that way is also a challenge. So one of the challenges that we have with hydrogen being used as a fuel in fuel cells is the ability to store it safely. So if we look at the advantages and disadvantages of fuel cells, the advantages are that we convert chemical energy directly into electrical energy, just like galvanic cells. The disadvantage is that they require a constant fuel supply from an external source, so we need to be continuously feeding them with oxygen and hydrogen in order for them to continue to run. There's no CO2 produced or sulfur dioxide or nitrogen dioxide. Okay, we want to avoid the use of the term greenhouse gas here because they do produce H2O, and H2O is a greenhouse gas. So if you say that they don't produce any greenhouse gases, you will be penalized in VCAR exams because water is a greenhouse gas as a vapor. So we want to keep it to emissions such as carbon dioxide, sulfur dioxide, or nitrogen dioxide. Carbon dioxide, of course, contributing to the greenhouse effect and ocean acidification. SO2 and NO2 being contributors to acid rain and other air pollution. One of the problems with this is while the fuel itself, the hydrogen and the oxygen, we can use oxygen from the air, is quite readily available, they do use expensive electrolytes and catalysts, which means that the initial purchase price and maintenance cost of these cells is high. They generate electricity as long as the fuel is supplied, so they won't go flat. So as long as you can supply fuel, they will generate electricity. This electricity, though, is DC. It's direct current, and the majority of the energy that we use in our homes is AC, so we'll need an inverter. This is much the same if you've had any experience with solar power. You need an inverter to use that solar power in your home. We can use a variety of fuels, not just hydrogen. Okay, so methanol and other fuels can also be used in these cells. But the effectiveness of these cells is highly influenced by things like purity. The presence of impurities in our fuels can poison the catalysts and reduce the life of those expensive electrodes as well. We can generate electricity on site, so because we can have continual supply of electricity without fluctuations in load and things like that, it's a steady electricity supply, which means it takes away reliance from a grid. Again, I'm not going to go through this in detail, but we make these comparisons between a fuel cell power production and coal-fired, one of the greatest being efficiency, remembering that coal-fired is only 30 to 40% efficient because we have significant losses due to transformations along each step. Coal is cheap, okay, but that is changing over time as our view on the environmental impact of coal changes as well. So what I want you to do is, we said we needed to be able to talk about the design features and the comparisons of these, is to actually review this and look at your notes and come up with a comparison between primary and secondary cells and fuel cells. Okay, so these are, remember that all of these cells, both primary, secondary, and fuels, are all galvanic cells. Okay, so our cathode is going to be positive, our anode is going to be negative while they are discharging. Okay, we're going to be having chemical potential energy into electrical potential energy. Just one quick thing before I finish up here is I want to show you a typical question from VCAR that looks at a fuel cell. This is from the 2015 exam, and it shows that a car manufacturer is planning to sell hybrid cars powered by a type of hydrogen fuel cell connected to a nickel metal hydride battery. And then they give us a diagram. This battery here is a red herring. This is here to confuse you and make you think that it might be electrolytic. It is a fuel cell. Okay, and the fuel cell is going to charge this battery. So we need to remember that this is going to be galvanic. So our anode will be negative and our cathode will be positive. Hydrogen is here and coming in, so this is going to be the combustion, so at our anode, and then our cathode is where oxygen comes in. This is a hydrogen-oxygen fuel cell, so the only product that we will get out is water. We're given the overall cell reaction and we're asked to indicate the polarity of the anode and cathode, which we have already done, and identify the product C. Done. We're asked to write an equation for the reaction that occurs at a cathode when the switch is closed. Okay, so if we think about that now, what we're going to do is we're talking about now we're going to close this switch. So this is going to now come in here, and then we're asked to figure out what's going to happen at the cathode when that happens. As I said before, this is not going to be recharging. It's a fuel cell, so it's not a secondary cell. So don't let this fuel fool you. All it's going to do is close the circuit. Our fuel cell is now going to operate. Our electrons are going to move up out of the anode through and down into the cathode. So we are going to have the reduction equation here. Okay, in this case, it has not said that it is alkaline. We have a polymer electrolyte membrane, so this is not an alkali electrolyte. So we're not going to use the OH equation. So we're going to go to our electrochemical series and find the equation for the reduction of oxygen. If we go and we find that, we will find that it is O2 gas plus 4H plus, which we can use because it's not alkali, plus 4 electrons goes to 2H2O, producing the H2O at that electrode as we suspected. We're also asked to list one advantage and one disadvantage of using the cell instead of a petrol engine to power a car. Okay, so petrol, remembering this here, if you think about it, it's trying to trick you up. Most of you are going to memorize that fuel cells require a continual form of, a continual source of fuel in order to operate. Okay, petrol engines do as well. If they don't have fuel, they don't work. So we can't use that in this answer. The advantage, of course, compared to a combustion engine, which only gives us 20 to 30%, is going to be a higher efficiency. Okay, which is going to be, up to approximately 80%. That's one advantage. You could also mention that there is no CO2 or particulate emissions, would be another advantage. As for disadvantages, higher cost due to the cost of the expensive electrodes. And remember, this was a hydrogen, so storage of the H2 fuel will be risk of explosives. Okay, so with these, there are a couple of things where they'll try and trip you up, but you should be pretty okay. Okay, that's it for fuel cells. Hopefully that makes sense, and I'll see you in class.